Section 5.8, Combinations and Probability. Mr. Wilcox decides to randomly select 3 students' homework papers from a statistics class to grade. He puts all 28 names in a hat. He mixes them up and draws out 3 names one at a time. We saw a problem similar to this in the last section where we did a permutation of 28p3, which ended up being 28 times 27, 26. However, for this problem, that's not the correct way to solve it. And the reason that it's different is because this problem is a combination instead of a permutation. And in combinations, order doesn't matter. So let's say we chose these 3 students in that order. That's no different than choosing the same 3 students in a different order. So in other words, if we pick 3 students in any order, right, we're still grading those 3 students' homework assignments. So let's tie this into the multiplication counting principle. If we're talking about those 3 students whose homework is getting graded, they can be chosen in 6 different ways because there's 3 possibilities for that first pick, 2 remain for the second, 1 for the third. So there's 6 different combinations where those 3 students can be chosen. And that applies to any 3 students, not just the ones that we're talking about in this example. As we mentioned already, the order that he chooses these papers doesn't actually matter. So we have to take the way we did this problem previously, 28 times 27 times 26, and divide it by the fact that there's 6 different ways to get that same arrangement of 3 students. So instead of getting the large answer that we got when we were doing a permutation, 28 times 27 times 26, it now gets divided by the number of different ways that it can occur. So again, combinations, the order doesn't matter. Permutations, the order does matter. When we write the combination in its math notation, we write it as 28C3, C for combination. A lot of times we'll say 28 choose 3 for combinations, 28 pick 3 for permutations. Another way that some people write combinations is like this. Inside a set of parentheses, 2 numbers stacked on top of each other. The first is the number of items in our group, and then the second is how many we're choosing from that group. The mathematical equation for a combination is similar to a permutation, but just a little bit different. So for a permutation, we had n factorial on the top, n minus r factorial on the bottom. You can see that here. And the only difference is now, in addition to that, in the denominator, we have an additional r factorial. How many items we're choosing, factorial gets placed next to that parentheses. Now, most lotteries are combination problems because you have to choose the right numbers, but they can come up in any order. So in New Jersey's Pick 6 Lotto game, a player chooses 6 different numbers from 1 to 49. They're selected at random, and if you match all 6 numbers in any order, you win the jackpot, which starts at $2 million. How many different possible sets of winning numbers are there for this game? So this is a combination because order doesn't matter. If you match the 6 numbers, you win regardless of the order that they show up in. We have 49 numbers that we're choosing from, and of those 49, we're picking 6, or choosing 6. And we can just plug that into our combination equation there. And we get 13,983,816. Now we're going to change the wording of the question. And instead of asking how many combinations of winning numbers are there, it's saying what's the probability that a player wins the jackpot by matching all 6 winning numbers. Well, we'd start off the same way. And we find out what the number of combinations are. And if we buy 1 ticket, our probability of winning is just 1 out of that number. So we can see that it's very, very unlikely for us to win the lottery. Our calculators might give this in scientific notation instead. So if you see a number that looks kind of weird, look for an E there. All right, and that means times 10 to the -8th power. There are 28 students in Mr. Wilcox's statistics class, 16 seniors and 12 juniors. Suppose Mr. Wilcox randomly selects 3 students' homework papers to grade. Use combinations to find the probability that all 3 students chosen are juniors. All right, so this is a probability problem, so this will be a fraction that we'll want to simplify to a decimal. All right, and the way we figure out what that fraction is to take the number of outcomes in event A and put it over the total number of outcomes. Event A is when we have 3 juniors being chosen. So to start, let's figure out how many ways can we choose 3 juniors out of the 12 total juniors. Okay? It doesn't matter what order we pick them in, so that would be a 12 choose 3. On the bottom, we're going to put in the total number of ways that we can pick any 3 students from the class. There's 28 students in the class. We're going to choose 3 of them. Again, order doesn't matter, so 28 C3 on the bottom. And we end up with a probability of 6.7% that all 3 students chosen are juniors. An airline has just finished training 25 junior pilots to become captains. 15 are male, 10 are female. However, only 8 captain positions are available right now. So the airline managers announced they're going to use a lottery to determine who gets those positions. They put all the names on pieces of paper, put them in a hat, mix them up, and pull out 8 names to assign those positions. When they announce the results, 8 captains are chosen, 5 are female, 3 are male. Some people are suspicious since the overall group of pilots had more males than females. Now, the first thing we're asked is how many possible groups of 8 captains can be selected. There's 25 captains in total. We're choosing 8 of them. Order does not matter. So there are over 1 million possibilities for groupings of 8 captains chosen from a total of 25. Part B, find the number of ways in which a fair lottery can result in 5 female and 3 male pilots being selected. Now the and here is the same and that we've seen throughout the chapter, meaning that this is going to be a multiplication problem. We want to choose 5 females out of the 10 that were in the group, and then 3 males out of the 15 males in the group. Each of these combinations gets multiplied together because of that word and there. And we see that there are 114,660 ways that we can choose 5 female and 3 male pilots. Now, the people that are suspicious about the results of this lottery want to know what's the probability that we end up with 5 female pilots and 3 male from this group of 25. We're going to use the combinations that we just calculated in parts A and B. So the number of ways that we could get 5 female and 3 male pilots was given by this set of combinations here. And then the total number of ways that we can assign these 8 pilots to positions from the group of 25 is this denominator here. A probability will always be a fraction that we can simplify to a decimal. So there's about 10.6% chance that we could assign these 8 roles and end up with 5 female pilots and 3 male pilots. So the last question here is this probability unlikely enough for us to be suspicious about how these roles were assigned? And the answer to that is no, because this is not an unusual probability. Unusual probabilities typically start with probabilities below 5%, although that's not a hard rule. We can adjust that depending on the subject matter that we're talking about. So this can happen by chance in about 1 out of every 10 times that we were to assign these roles. That's not unusual enough for us to be suspicious about the process that was used.